Hi, everybody. We have a good crowd today. 1, 2, 3, 4, 5, 6, 7, 2. Good. So we are ready to start. So what we are going to do today is finish our discussion on discrete time systems. It's one of the basic tools that we need to understand so that we can handle various tasks when we design control systems. For example, we may use a model, a discrete time model directly in controller design, or we may take a continuous time model, design the controller, and then discretize the controller. Or we may use a discrete time model in a multivariable controller, which is going to be the last part of this course, the most exciting one, actually, the real advanced control part for multivariate systems. So it's, again, one of the basic tools that we are dealing with. We are now on section 11 of the discrete time systems PDF. So very, very quick summary of what we are doing here so we can have a good context. So we have our process and our controller, our process and our controller. The controller sends commands to the process produces an output. We take that output perhaps with some noise, and from continuous, we go to discrete, analog to digital. So that goes to the controller. The controller will get some commands like the set point or maybe some constraints, as we are going to see in multivariable systems. And then when the controller generates a command, it's in discrete time. So we have a digital to analog converter, and that goes to our process. The process experiences the continuous time signal, and the controller understands the world in discrete time. So all this happens inside our digital device. That can be a standard PID device. It can be perhaps part of a SCADA system or part of a PLC system. There is convergence and overlap, actually, of digital devices these days, which can deliver all of these things. The idea is that the controller will have a measurement, perhaps a noisy measurement. It will have the external commands to the controller, and it will send a command to the process here, as I already mentioned. Other things like sensors, final control elements, valves, and all these things, I'm omitting here, assuming that they can follow the dynamics, their corresponding dynamics a lot faster than everything else. And of course, there are external disturbances that they go to the process. So one more time, we've done this several times. This is a continuous signal. After it is discretized, here it becomes a discrete time signal, so at specific points in time. The controller here generates discrete commands at specified points in time. Actually, let me make some space. Here it generates commands at discrete points in time, and then the input to the process is the staircase pattern, which has the zero order hold property, zeroth order actually. So it holds each value for the corresponding interval, and that's what happens here in the closed loop. The controller understands the world like this, basically. The controller is a discrete device. It understands that. And I have lumped perhaps the sensor here inside the controller. It could be if I have a discrete sensor, maybe it's like that. The controller takes a digital signal, produces a digital signal, and maybe it sends a discrete time signal out, and there is a DA separate in the final control element. The process, on the other hand, is continuous time. So, sorry, yeah, it's like this. So that's what the process understands. We can go from blue to yellow very easily, and we have two basic ways in which we can design simple controllers. One is take blue, so take the continuous time. So the continuous time model or continuous time information, that gives me a controller, and then discretize the controller. Or we can have a discrete time model. And from that, we get directly a discrete time control. Okay. To do all that, we explained how we can do things. For example, how from this we can go to that. Well, we spent the better part of the course already explaining how we can design a controller in continuous time. We can do it by trial and error. And I'm talking about the control law, assuming we know what we measure, what we manipulate, where is the feedback loop, and we only care about the control law here. So we can do this controller design by trial and error, having a PID structure, or we can use IMC, or we can use Ziegler-Nichols or IMC tuning for a PID structure. All of these we examine in great detail. Those are standard techniques that people use. We can also design things in discrete time directly. So we can have a discrete time model, and we can design a discrete time controller directly. We'll see a little bit of that today, so we can see how this can be done. Why is this a good idea? It's a good idea because it doesn't involve any approximation. Here, we may use approximation. This doesn't include an approximation. It's a simple technique for how to design controllers like this. In section 11, we already explained on page 20 how we can go from a continuous time model to a discrete time model. It's a mechanistic way. We don't need all that theory. We can keep it to the bare minimum for something very simple. So we already know what a continuous time model P of S means. For example, if it's first order plus time delay, like this. And we know what is the corresponding differential equation that connects U to Y. If we have here this P of S, we know that we have Y prime of T plus Y of T is equal to K U T minus theta. Is something going wrong, or is this random? Anything on chat? No? Okay, just messages. Sorry about that. Go back to our regular task. Okay, so it turns out, as we explained last time, that this, which is a model that tells us if I have an input like this, I'll have an output like that, according to either this model in Laplace domain or this model in the time domain. Rather than doing this, and approximating, I can find directly a transfer function G of Z that says, I'll write it in a second, but I'll explain what this transfer function does, actually, let me put it here. It says if you throw an input signal that is this staircase pattern, it has, and I know these values. This is my U, and this is T sub K. So T0, T1, etc., etc. This will give me an output Y that is something like this. And it's going to have these values at these points. Keep going. It turns out that I can, this equation here, which is continuous, or this equation here, which is continuous, it's in continuous time in the Laplace domain, connects this continuous signal with that continuous signal. Well, I can have an exact counterpart that connects only the dots, and it says the dots are connected according to a transfer function that has the following simple form, and this is in equation 31 and 32 in the notes on page 20. I'm just going to copy it from there. So this says that g of z, the corresponding transfer function in the z domain, is this k 1 minus e to the minus t over tau. T is the sampling period, divided by z minus e to the minus t over tau, e to the minus theta over t, assuming this is an integer. If it's not an integer, we take the nearest integer, and then we have a little bit of approximation, but nevertheless, if this is an integer, this is exact. And this tells me that there is a corresponding equation here, which is now discrete in time. And it says yk plus 1 is equal to e to the minus t over tau yk plus k 1 minus e to the minus t over tau times uk minus theta over t. So now this is my discrete time equation, and this has terms like A and B. And in practice, I will identify those terms from an experiment. Okay. And those, again, we have mentioned this a number of times. You can approximate the exponential. This e to the minus t over tau is approximately equal to 1 minus the first order term. And this b here then has k1, so it's approximate. Let me write the whole thing. So this is A, which is equal to this, B, which is this, which is K1 minus 1 plus T over tau. This cancels, so this is KT over tau. And these approximate formulas that we get here are the formulas that we would get if we wanted to go directly from this model here to the discrete time model here by simply substituting the derivative by finite divided difference, which we have done before. Good. All that is nice. Let's do one more thing. What is the steady state gain of this process in discrete time? So we have that. Let's go here. Yk plus 1 is equal to A yk plus B uk minus the time delay. Let me call it D. This here is the delay. So the steady state gain means if I change this by a constant and make it, let's say, M, this output Y eventually will go to Y infinity. Well, Y infinity plus 1 is just Y infinity, which will be AY infinity plus BM, which means Y infinity is, help me with the algebra. Yeah. And this is my steady state gain, right? This is the steady state gain of my process, let's say KP, which I can get directly. Here's another quick shortcut. I can get steady state gains can be obtained quickly from this equation here. Steady state gain is G at 1. Remember, for continuous time systems, the steady state gain is equal to P at S equal to 0. You put S equal to 0, you just get the K. Okay, this is just K. In fact, I'll remove the P so I won't confuse you. It's the same K that connects A and B. Okay, that's interesting math. That's fine. Can we do something so we can see this in action and how this might influence our controller design and all that? Well, let's see. Everything that we learned for controller design with IMC also carries forward to controller design with IMC for discrete time system. Exact same idea. But we have to be careful with what kind of G of Z we deal with. And that depends now on the sampling period. Let's see example 10 in page 21. So we can see what happens if we have a continuous time system. So we have a continuous time system, 6, 1 minus S, S plus 2, S plus 3. How do we get such a continuous time system? Well, we said there is an indication of this actually earlier on in the notes, and we covered this also in the previous set of notes. We'll defer the mechanics because we'll be bogged down by the algebra. There's plenty of algebra which is simple but tedious, that's all. So let's just say that this comes from two differential equations, two inputs, two outputs. Two inputs, U1, U2, two outputs, X1, X2. We'll cover this in multivariable systems in more detail. Take my word for it for now, just so we can make some progress and not waste all of our time doing algebra. So this is a transfer function. Do I understand how this connects the input U to the output Y? We have mentioned this already. If I put my 6, 1 minus S, S plus 2, S plus 3 here, I can find the differential equation. I'll multiply by the denominator, and I'm going to have something that has YW prime of T plus blah, blah, blah. It's something that has U on the right-hand side. Okay, it's going to have U prime of T and U of T and other things. Okay, let's not waste our time doing that algebra. Let's concentrate on this. What am I trying to do with this now? I'm trying to see how I would design a controller if I sample that system every T time units. And I designed the controller directly using, say, the IMC method. Okay, let's try to do that. So I need to find a corresponding transfer function G of Z, which is going to be the counterpart of this P of S for this corresponding sampling period T. How am I going to do that? How am I going to find G of Z? Well, we have the formulas in equations 31 and 32 in the notes. So let's apply these formulas. First of all, this is simple. I'm going to split this second order transfer function into a sum of two first order systems. The denominators are going to be s plus 2, sorry, this, and s plus 3. Is this for second order system stable? Yes, it is stable. Good. Why is it stable? Yeah, it has two poles. Which ones? Excellent. -2 and -3. Okay, very simple to say that this is definitely stable. And why am I asking this? Because I'll use the IMC method in the to design a controller, and the IMC method requires a stable system. So I could design an IMC controller for the continuous time system, but I want to do it directly for the discrete time system, so I can see what issues may arise if t takes different values. So I have to split this, as I already started saying, into a sum of partial fractions. I'm not going to redo the algebra here. It's plus 18 and minus 24 for these two coefficients. And by now you know how to do that. We have done this together, and the first homework actually teaches you how to do that. Okay. All right, then that means, oh, sorry. So this is P of S, which implies, apologies, that G of Z now is going to be equal to the formulas that I have in equation 31. So I have in equation 31, let me copy equation 31, that B over S plus A has a counterpart in discrete time, which is B over A divided by 1 over A, sorry, no, I copied the wrong one. It's B over A like this, multiplied by 1 minus e to the minus at, z minus e to the minus at. Okay? So the counterpart of this in discrete time and the counterpart of that in discrete time are going to be what? Help me with the algebra. This is my formula. I'm applying this formula to these two transfer functions. My B over S plus A is this in this case, and it has this corresponding G of Z term. Help me with this term. 18 divided by 2, yes. Excellent. Negative 2t. And the other term is? Going?
1 minus e negative divided by z.
Very good. And by simply looking actually at this formula here, we can tell immediately.
Professor,
Yes.
here,
Question?
it's okay. Sorry.
You cannot be heard very well. Let's see. Can you type your question on chat?
No, never mind. Never mind.
I'm sorry? It's clear. Oh, okay. Good. Feel free to interrupt me at any point. If you have any questions, actually, and there are issues with connection, try chat. It will pop up so I can respond. But thank you for participating, actually. This is great. All right, so far so good. Before we continue, a general result, the pole here, the pole of this term is equal to what again? In continuous time? Minus A, yeah. The pole of this is what in discrete time in the Z domain? It's the value of Z that makes the denominator 0, right? What value of Z makes the denominator 0? Yeah, it's trivial, right? It's then minus AT. So in general, if I have a pole P in continuous time, I have e to the PT in discrete time. It's a general result. Whether real or complex, it doesn't matter. It's the same thing. Same formula. Of course, complex poles appear in pairs, and they're going to appear in pairs in discrete time as well. And this also explains to me what I can consider stability in discrete time. A pole corresponds to stable behavior if it is in the left half of the complex plane, right? If it is here in the complex plane, this is the real axis, this is the imaginary axis. Now, let's look at this. If the pole is real, then if it's negative, the system, the corresponding behavior is stable in the time domain when you invert. That means for this corresponding pole in discrete time, I'm going to be between 1 and minus 1, right? Actually, 0 to 1. Yes, so I'm going to be here. 1, 0 to 1. And if the pole is complex, well, it's going to be negative. So I'm going to have e to the to a complex number here. And it turns out that this pole being negative, having a real part that is negative, gives me values that are here in the unit disk. This is called unit disk. It's a disk that has radius 1. And if a discrete time pole is there, then we have a stable behavior. If it's outside anywhere, we have unstable. So outside is unstable, inside it's stable. In continuous, this is unstable, this is stable. Let's continue here. So these two poles are what? E to the negative 2t, e to the negative 3t. Is this always going to be less than 1? Yes, right? It's it's 1 over e to the 2t. Always less than 1. It's actually greater than 0. But this part is irrelevant. This is the nice part about stability, the right-hand side. In fact, I should put it here, the less than 1. And same thing for this 1 over e to the 3t is less than 1. Nice, this is nice, stable pole. There is more interesting behavior, though, with the zeros. Because if I take this g of z and lump it into one transfer function, and I have done the algebra, but I see that I didn't include it in the notes. So I'm going to leave that as a homework, not to hand in. You know how to add two fractions that don't have the same denominator, right? So the numerator is going to have something times z minus something, and the denominator is going to be z minus e to the minus 2t, z minus e to the minus 3t. So this is my g of z. The interesting part now is that this system here has a 0, which is equal to, well, the poles We already wrote where the poles are. Okay. So pole 1 is this. Pole 2 is equal to that. But 0 is at the point Z1 is equal e to the negative 2t plus e to the negative t minus 8 e to the 2t e to the t minus 8. You see that this is somewhat clunky 0 in the sense that it doesn't have a nice clean counterpart in the continuous time like these two here, the poles. The poles are nice and easy, but the zeros are more elaborate. And how the poles behave if t, the sampling period, changes is simple. So I will copy this from the notes and I'll plot it here. If the sampling period changes, the poles, well, they go to 1, but they never reach 1, so asymptotically they go to 1 and they drop e to the negative 2t, e to the negative 3t. They drop like this, and this is 0.5, 1, 1.5, 2. So they behave like this. You can tell that there's a general behavior here, poles close to 1, poles close to 0. There are issues with both ends here. If I have a pole close to 1, that says my system contributes something which, when inverted, is going to give me 1 to the k, something that's about 1 to the k, which is a constant, right? Same thing if it's close to 0. If the pole is close to 0, I'll get something 0 to the k. That says if I sample either too fast or they're too slow, if the sampling period is too small or too large, I get either no dynamics, everything is constant, or again, no dynamics, nothing changes. It's all at the initial value, okay? So which is why it makes sense to be here somewhere in the sampling period. I cannot sample too fast or too slow. It's very important. Things get even more interesting, even more exciting when I try to look at the 0 of my system, because the 0 of my system is as follows. This is t. This is the 0. Well, let me just call it 0. And it's from 1 asymptotically again, 1, but there is, this is 0.5, 1, 1.5. It is asymptotically above 1, but then it comes back to 1. There is an asymptote here. So if I try to design controllers for sampling periods in this range, or sampling periods, all sampling periods in this range, let's say that t is equal to 1. Let's try to do this. So t is equal to 1. 1 appears to be okay here, right? As does 0.5. I have something like this here. So let's take which sampling here? 0.5 here. This is a good one. So let's try to design a controller based on 0.5 and see what problem we may encounter. So if I try to design my controller based on this sampling period, my transfer function in discrete time, help me with this, it's this one here. So it's going to be 18/2, so implies G of Z. What am I going to do now? Let's first of all make a plan. What I'm going to do is put t equal to 1 here, create a transfer function, and use the IMC method, the internal model control method, to design a controller and see what controller I get, and see if I can do the exercise or if I need to be careful with something or have modifications, right? Okay, let's execute the plan. So this is my G of Z, my discrete time controller. Again, I'm having this sampling period. Is this reasonable? Well, I get these values here for the two poles. It appears to be reasonable. It's fast enough. I need to program my PLC, so I need my G of Z so I can construct my design, my IMC, and put it in my PLC system, my programmable logic controller. Okay, so G of Z then from up here is going to be 9 times 1 minus e to the minus 1, z minus e to the minus 1, plus minus, let's say, 8, 1 minus e to the minus 1.5, z minus e to the minus 1.5. Somebody with a calculator can help me with these numbers? So this is 9 z minus what again? E to the minus 1? It's 0.63. And the numerator therefore will be 0.37. It was 0.63, how many seconds? I think 2? It doesn't matter, 2 is good enough for now. Okay, so is this correct? That doesn't look correct. E is 2.7,
Oh,
so
that's
1
right,
over
that's doing
2.
the top
Okay. Like that? Okay, that looks better. It's 1 over 2.7, right? So it's about 1.4. So 0.37 looks right. Okay, minus, let's try the other one also. The next term. 0.22 in the numerator or denominator. So 0.22 and the numerator is 0.78. All right. And let's do the algebra. Can you help me with the algebra here to put all this together? So it's going to be this times this here. So right? Multiply z minus 0.22 minus z minus 0.37. The denominator has z square minus 0.37 plus 0.22 z plus 0.37 0.22. First of all, is my algebra correct? I'm not looking at a cheat sheet. I'm doing this on the fly. Good. And let's do the whole thing in the numerator. So we have 5.67 minus 6.24, right? Z minus, help me with this, 5.67 minus 0.22. What is that again? This times this. 1.21, 2.5. And then it's plus 6.24 times 0.37. 2.31. Okay, divided by z square minus 0.59 z plus 0.37 times 0.22 is how much? .08. Okay, one more digit. 1. Okay. All right. So, and then the numerator finally is so it's 5.67 minus 6.24. It's minus what? Okay. And this is plus 6, 1.06. All right. The denominator is the same. So this is my transfer function. Now, remember when we did our IMC design? Well, we can apply the IMC design here, so we can design our beautiful controller. Why are we going through all that pain and don't just introduce something to our PID control system directly from the reset time, integral time, and derivative time and gain? That's because certain systems allow you to put directly the difference equation into your control system, into your PLC, which is very, very easy to program, like Excel, like an Excel line. Okay? So it is meaningful to do this, and it took us a little while here because we are doing this for the first time. Once you see how this is done, it's all algebra and it's done very, very quickly, especially if you want to mechanize it. So let's do the IMC design. Then for this G of Z, I'll write it again. Well, for our IMC design, we have that G of Z would be, put G here, and now I'm going to have my controller Q of Z, and I have my model here, which in general won't be the same, but for my design at this stage, I assume they are the same. And I do here minus, this is my set point, and this is my input unit. This is my IMC feedback loop, and there may be a disturbance. Here, there may be noise. Here, there may be other things. And we know how to design our controller. If we have our G of Z, the target for Q of Z is to make this approximately equal to 1 over G of Z, right? But to make this approximately to 1 equal to 1 over G of Z means that we have to make this Q equal to 1 over G of Z times a filter. Well, the filter in this case, a first-ordered discrete time system, is the counterpart of the continuous time system. The counterpart in discrete time is 1 minus alpha Z minus alpha. It's in the Z domain, so this is a simple filter. Alpha is a parameter that is between 0 and 1, so I can have stability and good performance. And everything I learned about IMC in continuous time carries over here to discrete time. The closed loop is just dictated by the filter and all that. Of course, what I learned in continuous time IMC is that the closed loop is stable if and only if Q is stable. The stability of Q is necessary and sufficient for the stability of the closed loop. Well, let's check. Is 1 over G of Z stable here? Well, this is my G of Z. So 1 over G of Z is what? It's this denominator, which now is in the numerator. divided by 0.57 z plus 1.06. Is it stable? Because the root of the denominator is what? The root of the denominator, the value of z that makes the denominator 0 is 1.06 over 0.57, right? That's about 2, right? Well, yeah, 1.86x, which is greater than 1. Is it inside the unit disk? Real, imaginary? No. It's here somewhere, right? Therefore, I cannot use this here, so I cannot use this. I have to find something else. Remember, in continuous time, we said if we have an unstable pole that gives me things in the denominator that have s minus a, I simply replace this by minus s minus a, and everything is dandy. Here, there is a different rule, which is described actually in the table 1 on page 23, or not page 23, page 25, actually, sorry, it's further down in the table. If I have 1 over z minus a, which is a is an unstable pole, I replace this by 1 minus 1 over a, z minus 1 over a. But let's do another, let's pick another sampling period for which we're not going to have this problem. Let's summarize, first of all, what we have done so far, so I can make sure we are following example 10. So what is example 10? Example 10 tries to show us how we can go from continuous to discrete, how we can design the controller directly in discrete time using IMC, and what issues may arise in discrete time and how to handle them. We've seen all of these things in continuous time. We'll do a little bit in discrete time. So let's continue our discussion. We started with this continuous time transfer function in the Laplace domain, which connects, of course, input and output this way through this second-order differential equation. From this continuous transfer function, we got a discrete time transfer function, which is in partial fraction form. I didn't do the algebra for the whole. Just make that just a rational fraction because it would fill out a lot of stuff here. It would be messy. So you understand where this is going on. And then we did a particular case when we selected t to be 0.5 and said, in this case, g is this, and IMC directly doesn't work for that. Well, can I choose a different time, a longer time period? Well, for all of these time periods here, I'm outside this band. So clearly, I cannot use values up to this point and derive a direct controller using IMC, but I can choose a larger sampling period, and then IMC is piece of cake because now the 0 is here, which is between 1 and minus 1. This is page 7 in the notes again, on page 21. Let's do this exercise together. What am I going to do now? What is our plan? We're going to see what is g of z for t equal to 1.5. We'll find g of z. It will be something. Well, it will be this plus that, which is going to be something. And then we're going to construct Q, which is going to be 1 over G of Z times F of, let me write it further down. So Q of Z is going to be 1 over G of Z, F of Z. And then we'll try to simulate that or try to understand what that means for our discrete time system. Okay, let's execute the plan. So G of Z is, well, I need to make this smaller. So it becomes a little bit messy. So it's this expression here for t equal to 1.5. So it's going to be 18 over 2, 9, 1 minus e to the minus 3, z e to the minus 3, plus minus 8, 1 minus e to the minus 4.5, z minus e to the minus 4.5. So this is going to be, let's go down now together. Help me with the calculations. So this is 9 multiplied by, what is e to the minus 3? Zero point 0498, let's say 45. And this is then 0.955, the numerator, times 9, right? So what is it again? 8.55. And the other one is minus z minus, what is e to the minus 4.5? Okay. And the numerator is 8 times 1 minus this, which is 7.91. And if I put these two together, it's going to be 8.55 z minus 0.01 divided by z minus 0.05 minus, so minus 7.91 z minus 0.045. And the denominator is going to be z square minus 0.045 plus, it was 449, you said, right? Okay. Or 498. Plus z plus the product of these two. And the numerator now is equal to, let's do this together. So it's 8.55 minus 7.91. So it's 46 point, right? Z. And help me with this times this plus this times this. Point 489, and it's plus or minus? It's what? Positive?
Positive 0.29.
This, right? Okay, now something like this,
No, that's
this. Okay, which means the 0 now in the numerator is at what point? It's at 0.299 minus divided by 0.64, which is about minus 0.5, right? Right? Yeah. Which means now if I take 1 over g of z, I can have my transfer function to be this, which I have from the denominator from up here, divided by 0.64 z plus 0.299, 1 minus alpha, z minus alpha, and this will give me my controller Q, and this I can live with, and I can now choose the values of alpha so I can have the corresponding closed loop response that I want. In fact, I can do all that and understand the closed loop response without doing much in terms of designing the controller, because I know that if I have the closed loop, y of z is g of z times q of z, y set point of z, plus 1 minus g of z, q of z times the disturbance, perhaps with things that have noise and all that. And because now q of z is this expression up here, I can just put this q of z there. And this will give me something equal to f of z, y set point of z, plus 1 minus f of z times the disturbance of z. Plenty of math. I try to go through the math with you so we can get to the final thing. The final thing is this. This is the final response that I'll have in my system. So I know that if I build this controller Q that I have here, then the output Y will respond to Y set point or external disturbances like this. Let's try to understand what this is and to visualize it. So what did we say the filter F is in the Z domain? Yeah, 1 minus alpha, Z minus alpha. It's up here, right? This is the filter F. Y set point plus 1 minus alpha, Z minus alpha, D of Z. Okay. I can do everything in the Z domain, but let's go back to the time domain to deal with differences in the time domain, because frankly, it's going to be very unwieldy to just do everything in the Z domain. Too much algebra, too cumbersome. How would I go to the difference equation that explains to me now how the closed loop behaves? Multiply by the denominators, as we have done it several times. So I have Z minus alpha, Y of Z is equal to 1 minus alpha, Y set point of Z, plus Z minus alpha minus 1 plus alpha, D of Z. These cancel, and help me go back to a difference equation in the discrete time domain. I take the inverse. When I multiply z by a y of z, a z transform, when I go back to the time domain, the discrete time domain, this is a sequence y at what point in time, in discrete time? Well, let's do the other one, this alpha times y. Alpha is a constant, so if I invert this y of z, I get the sequence y at time k, right? And if I invert this thing, this is a sequence 1 minus alpha is a constant. This is a sequence y set point at time k. And if I invert this, well, it's z minus, this thing is z minus 1 d of z. If I invert it, the 1 times z is just d sub k, and there is something in front of it. What about the index of this? If I have z times y of z, when I invert it, it's y at what point in discrete time? It's of the 3 facts we learned for z transforms, it's the 3rd fact. Can you look it up? It's also in the notes on page 16. It's what again? Yes. So this is what my closed loop is going to look like. It says yk plus 1 is alpha yk plus 1 minus alpha yk set point plus dk plus 1 minus, this is the minus 1, so minus dk. This is how the closed loop is going to behave. Alpha must be between 0 and 1. It cannot be above 1 because the closed loop will become unstable. And we don't want it to be below 0 because we'll get oscillations. Let's simulate this on Excel. It's so incredibly simple. We can simulate that closed loop on Excel. So this closed loop, again, what are we going to simulate here? We're going to simulate this closed loop here that I am showing in this schematic here. G and G tilde are equal to each other. This Q is this elaborate Q that I constructed here. We'll explain how to put this together, this elaborate Q. It's not difficult, but it's just busy work, that's all. So to avoid being bogged down, let's say we'll see how to program this in our system. We know G of Z already, so if we put all this together in our computer, and again, as we've said several times, this is all this is in our computer. Okay? This is our computer. It takes measurements, it takes set points, produces commands. If I put all that there, the closed loop will behave nicely according to this. Well, let's simulate this on Excel. It's very, very simple. So on Excel, we're trying to simulate. Oh, it's already started. This system, discrete time no, this one. So this alpha that we have there, this alpha is our one tuning parameter that we have in this filter for our IMC control. a rule of thumb, and this has to do with robustness, is make this above 0.7, 0.8. Otherwise, you may run into robustness problems. So I'll make this 0.8, but then we'll explore what other values mean for our process. So if this is what we have there, formulas, create a name for this. We have our system, which is K, YK. We can have a certain set point, a certain disturbance. We'll see how our closed loop behaves for this system. So let's say our system is 0, 1, etc. We can have a bunch of these. Initially, we are at 0. Remember, everything is at steady state in deviation form, so 0. The set point, we can consider a step change of magnitude 1. Disturbance, let's say no disturbances. Let's isolate things and we'll see what happens. So the closed loop behaves in the following way. Let's go back to our notes. The closed loop says, I have the next value of y depends on the previous value of y times alpha. Okay. So this is equal to alpha times the previous value plus 1 minus alpha times the previous value of set point plus the current value of disturbance minus the previous value of disturbance. Right? I haven't messed up in the algebra anyway, I hope. So what did we say again? It's the current value of disturbance minus the previous. So it's the current value of the disturbance, which is d5, minus the previous one, which is d4. Okay? So this is here. Let's make this same. Let's make this same. Let's try to plot this to see what we created here. So this. Okay. Insert the plot. This is good enough. Okay, so I don't even need all that, but first 50 values are good enough. So and like I said, I don't need all that. Let me just use 20 are good enough. Okay. Actually, this has 1, 2, 3. I don't want it like that. 1, 1, 0. Okay, bear with me and let me do it in a different way. This is better so we can have 0, etc. Like this. That's good enough. This is blue is my output. Let me do it yet one more time. Do it more easily. So This is better. This I don't need. 6. Put it here. Oops. Here. Okay. And this, we said 50 is good enough. All right. So what are we looking at again here? We are looking at a system where I have an IMC controller. The controller has explicitly the model G, the controller Q. We'll see how to program those in a minute because those are messy. But the closed loop is simple, elegant, and I know immediately what the one and only one tuning parameter alpha does to my closed loop. This alpha is 0.8. 0.8 means I have a closed loop that has these dynamics which are given by this difference equation. In fact, I can solve this difference equation, or I can do the inversion here, and that means the inverse of this part is going to be it's going to have alpha to the k because I have this pole there at alpha. It's like Laplace transforms that have the corresponding e to the something, the z transforms have the pole to the kth power. So alpha to the k will give me these terms here, alpha to the k, 0.8 to the k. If I make alpha equal to 0.2, let's say, is my closed loop going to become slower or faster? Well, I can understand this in many ways. Let me go to my time domain. For alpha equal to 0.8, I have that the set point influences the output, the previous set point, according to 1 minus 0.8. So it's a factor of 0.2. If I make alpha equal to 0.2, the set point influences by 0.8. Which is stronger influence? For alpha equal to 0.8 or alpha equal to 0.2? 0.2, obviously, right? Therefore, for smaller alpha, I'll have faster or slower response of the closed loop. Faster, exactly. Let's experience that. Bracket on to 0.2. Ta-da, I have my faster response. So that's fine. In fact, I can push it all the way and be unrealistic and have 0 and have this. That's called, it has the funny and fancy name, deadbeat control, because in one shot, you just have this response. People discovered this several times. It's like all good ideas that deserve to be discovered and rediscovered and rediscovered several times. Let me just put a few names. So Dahling discovered that a number for discrete time systems. He was trying to design controllers for electronics, actually, for hard disks and things like that. So he figured that's an easy way. Manfred Morari discovered this in the 80s, and I should not fail to also mention Carlos Garcia. Carlos Garcia was a student of Morari's. He was also in our industrial advisory board here at UH. A super nice guy and very supportive of the department and students and everything. Eula Kuchera discovered this a number of times in both continuous and discrete time. Others discovered this idea actually a number of times. Oh, and I forgot, Newton, Gould, and Kaiser, and I hope I'm not misspelling any of these names. They wrote a book, no less, in the 50s, no less, about this. They had it all there. I think the issue was that these three guys, Newton, Gould, and Kaiser, were electrical engineers, but very bright people. They were from MIT. They did a lot of work in the chemical industry. So I speculate, that's a wild speculation, that being electrical engineers working in the chemical industry, they were not taken seriously either by chemies or by double E's. That's why what they had in their book was never taken seriously. They had it all laid out in great detail there, how this can be done. Anyway, these ideas were discovered again and again and again in the 60s and the 70s and the 80s. They're commonplace now, they're included in undergraduate textbooks. Okay? So let's continue a little bit with our simulations here so that we can understand how this behaves. So if this was, like I said, 0, you would never do that. Of course, if this was minus 0.2, well, that would be a a negative pole. It's a real pole, but it creates oscillations. And it creates oscillations because it will give rise to minus 0.2 to the k. So it's going to be minus 0.2, so minus 0.0, sorry, plus 0.04, etc., etc. Let's visualize this. So you see these oscillations. These oscillations can be more pronounced if I make this larger. Negative, so you see these oscillations. This is not a good behavior for a closed loop, so that's why we avoid these values for alpha. That's why I said when I mentioned alpha should be positive between 0 and 1. For all practical purposes, actually, this should be 0.7 greater than alpha, less than alpha, and 1 greater than alpha. So if you make this to 0.7, you get a nice closed loop. That would be a nice, beautiful closed loop. We can do the same thing if we have a 0 set point change, and we have a step disturbance entering the system. So I have my step disturbance, and this is here. So this shows direct, oops, what did I miss here? Something doesn't look right. I have messed up something. I'll check what I messed up with. This shouldn't give me this. It's way too perfect. My set point is this. Is this? It shouldn't give me that. Let's try a random number. Let's see what my system does. So this is my y of k. You see that there is a random disturbance here. My controller brings the system down to its set point. It's a reasonable behavior to expect. The other thing is, I should go back. There was nothing wrong, actually. It's the fact that I have a perfect system that determines that it's a step, so I know how to reject that in one step. That's why I'm getting this, because of my perfect model. Okay. So this is what happens with IMC design. If we want to conclude the discussion, we should also mention what is included in example 12, which is an example that shows what is called ringing. What is ringing? Let's briefly mention that, and that will give us a closure of this discussion. Ringing happens when I have systems like the one we just looked at, the second order system. Let's look at the one in example 12, and we'll close out that very quickly. If I have the system P of S equal to this simple two first order systems in series, we get these all the time. If I discretize that at a reasonable time, I can get G of Z. This is with sampling period equal to 1. Gives you G of Z equal to 0.028 Z plus 0.0234 z square minus 1.54 z plus 0.587. Nice, simple, elegant. Stable, yes, stable. Can I invert? Is the inverse stable? Yes, except the poles are at minus 1.5, minus 1/3 in this. And in the discrete time, they are e to the minus 1/5, which is 0.85, and e to the minus 1/3, which is 0.69. Stable, stable, stable. Everything is nice and stable. The zero, however, is at minus 0.84, which is nice and stable, except the inverse will create terms in the closed loop that are going to have minus 0.84, or in the process input rather, process input, which is going to have these terms. So you go plus, minus, plus, minus, plus, minus, plus, minus for my process input. The simulation is showing the nodes and shows that if you have this closed loop, you think you're making a step change and your output y goes like this because you have these values here in discrete time. Except these are not, the continuous line I drew is not the right one. The real one is actually going to be something like this. That's what is called ringing. And that's because the input here, the input u, is going to be something like this when made in continuous time. So you may think these nice dots behave so nicely here, but in reality, they do not. You can avoid that by doing what is suggested in the notes, namely shifting the pole according to the recipe that I have in the lecture notes as given there. Okay. With that, I'm going to close this discrete time system discussion. We covered pretty much everything we wanted. There are more examples like 13 that we didn't do. Take that as a homework problem not to hand in, as we always do. And next time, we are going to cover identification, the reverse of this problem. If I'm given all these techniques, how on earth do I get a nice model so that I can use it for my super techniques that are model-based? That's a very exciting section of the course. And the nice thing is that there's plenty of software, and even Excel actually can give you plenty of good stuff. MATLAB is even better, but Excel is good enough for many occasions. I'll stop here and we'll continue on Wednesday.